Look at this. Stop. If you're thinking long division, put the pen down.
With exponents this high, long division is useless. You'd be here all day. We just need the remainder. We aren't here for busy work.
Look at the scale. You'd need hundreds of steps to finish. One tiny sign error at step 50 and the whole thing's ruined. You've wasted your afternoon. Brute force is a dead end. It's slow and messy.
We're gonna find a shortcut. We'll solve this in seconds.
But to find the shortcut, we first have to recognize the trap. Look at these exponents, 2026 and 2025. This problem is designed to look difficult. The standard move is the remainder theorem. Find the roots, plug them in, and you're done, right? Except for one detail. The roots of this divisor, they're a complex mess. We've got 4 roots on the complex plane, and they're messy, really messy. Do you really want to raise these complex numbers to the 26th power? I didn't think so. Then you've got a 4x4 system of complex equations. That's not math. That's inefficient. It's a mistake, a total time sink. We aren't falling for it. Forget the roots. Think about structure. Polynomials behave just like integers. In integers, we care about the remainder after division. In polynomials, it's the same thing. We need to reduce this massive exponent. The goal is to find a cycle. If we can find a power k where x to the k is 1, we can jump ahead by thousands of steps instantly. But does such a k exist for our messy divisor? That's the critical question. Look at this expression. It looks simple, but it's actually the key to factoring much larger powers. It's almost a perfect square. We're just 1x squared short of a clean factorization. So we're going to force it. Add x squared to finish the square, then subtract it to maintain equality. And there it is, a difference of squares. This is where the algebra really becomes useful. These factors aren't just arbitrary, they're the quadratic parts of our standard cube formulas. One pops up in the difference of cubes, the other in the sum. It's all connected. When you multiply them back together, it's beautiful. This whole thing is the core of x to the 6th minus 1. Since we're working modulo our divisor, that term on the right becomes 0. That's the cycle. Every 6 powers, the math resets to 1. It's that simple. Now we apply the shortcut. Since x to the 6th is just 1, we can shrink these exponents instantly. Every group of 6 in the exponent is just a factor of 1. It effectively just vanishes from the math. 2026 divided by 6 leaves a remainder of 4, so we're really only left with x to the 4th. Same logic for 2025. Strip away the multiples of 6, and you're left with 3. So x to the 2025 simplifies down to x cubed, a whole lot better. We just turned a difficult problem into something manageable. No more massive exponents to deal with. Looks simple enough, but if you stop here, you've made the final mistake. Think we're finished? Not even close. Look at that x to the fourth.
The rule, your remainder's degree has to be smaller than the divisor's.
They're both degree 4. The degrees are equal, so we can't stop here. One more reduction.
Since we're working modulo our divisor, we treat it as 0.
Shuffle the terms. X to the fourth is just negative x squared minus 1. Now swap that straight into our remainder.
The ones cancel out.
Perfect. Final answer, x cubed minus x squared. Done! No long division, no complex calculations, just logic. Huge exponents usually hide simple patterns. You just need to know where to look. I'm Matilda. Stick around to see how math actually works.